We often think of materials as fixed things. Wood is wood, steel is steel. They have properties we know. Wood is strong, but it burns. Steel is stronger, but it rusts. We learn these rules as kids. Don't touch the hot stove, don't drop the glass cup. We build our world on these predictable behaviors. But what if we could change the rules? What if we could make a material that is as strong as steel, but as light as plastic? Or a metal that's transparent, or a window that can repair its own cracks. For a long time, these ideas were pure science fiction. They were impossible, they broke the rules we thought we knew. The interesting thing is we are starting to make them. Not by magic, and not by breaking the fundamental laws of physics. We can't create energy from nothing. We can't build something that is in two places at once. The universe has hard limits. But we are learning that the space within those limits is much bigger and stranger than we ever imagined. The trick isn't to break the rules of physics. The trick is to be clever with them. We are learning to build materials from the atom up. We are becoming architects of matter itself. And by doing that, we are making the impossible possible. So where do we start? We start with the rules. The real rules, the ones we can't get around. Everything is made of atoms. Atoms are listed on the periodic table. You have hydrogen, helium, carbon, oxygen, iron, and so on. These are your building blocks. You can't invent a new kind of atom. Each atom has a certain number of protons, neutrons, and electrons. This defines what it is and how it behaves. Atoms like to bond with other atoms to form molecules. They share or trade electrons. These bonds are what hold the world together. The type of atom and the type of bond determine a material's basic properties. A diamond is just carbon atoms. A lump of coal is also just carbon atoms. The difference is the arrangement. In a diamond, the carbon atoms are locked into a super strong, rigid, three-dimensional lattice. In coal, they are arranged in messy, weak sheets. Same building block, different architecture, completely different material. This is the first big clue. The properties of a material depend not just on what it's made of, but how it's put together. This is true for everything. The strength of a brick wall depends on the bricks and the mortar. But it also depends on how you stack the bricks. A careful pattern is much stronger than a random pile. Physics also gives us other hard rules. The laws of thermodynamics are a big one. You can't get more energy out of a system than you put in. This means perpetual motion machines are out. A material can't generate its own power forever. Any material that seems to do work, like one that changes shape, has to get that energy from somewhere. Maybe it absorbs heat from its surroundings, or it reacts to light. The energy is always conserved. It just changes forms. So we have our Lego bricks, the atoms, and we have our rule book, the laws of physics. We can't change the bricks and we can't tear out pages from the rule book. For centuries, our ability to build with these bricks was clumsy. We could melt things down, mix them together, and let them cool. That's how we made bronze and steel. We could chop things up, like wood. We could grind things down, like stone. We were working at a large scale. We were manipulators of bulk materials. The idea of placing individual atoms where we wanted them was not even a dream. That has changed. This is the whole key to making impossible materials. We have developed tools that let us see and move individual atoms. We can build structures on a scale of nanometers, which are billionths of a meter. This field is called nanotechnology, and it's where the magic starts to happen. When you can control the architecture of a material at the atomic level, you can give it properties that it would never have naturally. You can build a wall where you choose the position of every single brick and design the mortar between them. Let's talk about one of the most famous examples of this, invisibility. For as long as we have told stories, we have dreamed of being invisible. It seems like the ultimate violation of the laws of nature. An object is visible because light bounces off it and hits our eyes. To be invisible, you have to somehow guide light around an object, as if it were never there. The light has to come out the other side perfectly, with no distortion, like water flowing around a smooth stone in a stream. No natural material can do this. If light enters a material, it either gets absorbed, reflected, or it passes through but gets bent. Think of how a straw looks bent in a glass of water. That bending is called refraction. Every material has a refractive index. Air has one, water has one, glass has one. They are all positive numbers. To make an invisibility cloak, you would need materials with a negative refractive index. You would need to bend light the wrong way. For decades, scientists thought this was impossible. No known atom or molecule behaved this way, but then some scientists had a clever idea. What if it's not about the material itself, but about its structure? What if we build an artificial structure smaller than the wavelength of light itself? This structure could be made of normal materials, like tiny bits of copper and fiberglass. But we could arrange them in a precise, repeating pattern. This pattern of tiny metal rings and wires could interact with the light wave passing through it. The light wave doesn't see the individual copper atoms, it sees the overall structure. And this engineered structure as a whole can have properties that its constituent parts do not. This new thing is called a metamaterial. Meta means beyond. It's a material that gets its properties from its structure, not its composition. And it works. Researchers have built these metamaterials. They are typically flat panels made of a grid of these tiny electronic structures. They can take a beam of microwaves and bend it backward, a negative refraction. They can guide waves around an object hidden behind the panel, making it effectively invisible to microwaves. Now, we are a long way from a Harry Potter style invisibility cloak. Making one for visible light is much, much harder. The wavelength of visible light is tiny, so your engineered structures have to be even tinier. And you have to make it work for all the colors of the rainbow at once and from any angle. We are not there yet. Current versions are very limited, but the principle is proven. We can make something that seems to break a fundamental rule of optics. We didn't change the physics of light. We just built a very clever maze for it to run through. This idea of structure over substance opens up a whole new world. We take strength. We want things to be strong, but we also want them to be light. This is a constant battle in engineering. If you want to make a stronger airplane, you typically use thicker metal, which makes it heavier. Heavier planes need more fuel. It's a trade-off. For decades, we looked for stronger and lighter materials by mixing metals to make new alloys. Or by creating composites like carbon fiber. These were big steps forward, but now we can go to the atomic level. Consider graphene. This is one of the most hyped materials of the 21st century, and for good reason. Graphene is a sheet of pure carbon. That's it, just like diamond or coal. But in graphene, the carbon atoms are arranged in a perfect, flat, hexagonal lattice. It looks like a honeycomb, and it is only one atom thick. You can't get any thinner than that. Because of this perfect structure, the bonds between the carbon atoms are incredibly strong. A sheet of graphene, if you could make one the size of plastic wrap, would be stronger than a sheet of steel of the same thickness. In fact, it's the strongest material ever tested. A single sheet would be almost invisible, yet it would be strong enough to support the weight of a cat. It's also incredibly light. A square meter of it weighs less than a milligram. It also conducts electricity better than copper and conducts heat better than any other known material. So here we have it. A material that is super strong, super light, transparent, and a great conductor. It sounds impossible, but it's real. We can make it in labs. The problem is making it big. Peeling off a tiny flake of it in a lab is one thing. Manufacturing it in large, perfect, affordable sheets is a massive engineering challenge. We are getting better at it, but we can't just build a bridge out of graphene yet. We are learning how to mix tiny flakes of it into plastics or other materials to make them stronger and lighter. We are in the early days of a graphene revolution, and graphene isn't the only one. If you take that one atom, thick sheet of graphene, and roll it up into a tiny tube, you get a carbon nanotube. These are also unbelievably strong for their weight, so strong that they are the only material we know of that could, in theory, be used to build a space elevator, where you run a super strong cable from the ground all the way up to a satellite in orbit. Then you could just send elevators up the cable into space. No more expensive, dangerous rockets. It would change everything about our access to space. Right now it's a dream. We can't make a carbon nanotube that is long enough, strong enough, or perfect enough for that cable. A single mistake in the atomic structure, a single missing atom, could create a weak point that would cause the whole thing to snap. But 30 years ago, the material to even dream about this didn't exist. Now it does. The problem is no longer theoretical physics, it's practical engineering. Let's think about another impossible combination. Something that is extremely light, yet also a fantastic insulator. The best insulator we know of is a vacuum. No atoms, no heat transfer. But you can't build a house out of a vacuum. You need a structure. This led to the invention of aerogel. It's sometimes called frozen smoke or solid air. It looks ethereal, like a faint blue cloud you can hold in your hand, but it's a solid. Aerogel is made by taking a gel like gelatin and carefully replacing all the liquid inside it with a gas. What's left is the solid scaffolding of the gel. It's a delicate three-dimensional network of silica, the same stuff glass is made of. The final material is over 99% air. It is incredibly light. A block of it the size of a person would weigh less than a pound. And because it's mostly trapped air, it's an amazing insulator. You can hold a piece of aerogel in your hand and put a blowtorch to the other side, and you won't feel a thing. The heat just can't get through the complex tangled structure. NASA has used it to insulate electronics on its Mars rovers. They've used it to capture dust particles from a comet's tail. The dust particles, traveling at incredible speeds, slam into the aerogel and are slowed to a stop without being damaged. The material is so light and delicate that it acts like a foam cushion for speeding bullets. Here again we have a material with properties that seem impossible. A solid that's as light as air. An insulator that can stop a blowtorch, and again, it's not because we invented a new magic atom. It's because we figured out how to build a very specific, very strange structure out of a very common substance. The next frontier is to make materials that are not just passive, not just strong or light or insulating, but active. Materials that can change, that can react, that can even think in a way. Think about self-healing materials. When your skin gets a cut, it heals itself. Your body sends platelets to form a clot, and then new cells grow to fill the gap. It's a complex biological process. Could we make a man-made material do the same thing? The answer is yes. There are several ways to do it. One approach is to embed tiny microscopic capsules into a material like a plastic polymer. These capsules are filled with a liquid healing agent. A second type of catalyst particle is also mixed in. When a crack forms in the material, it ruptures the capsules. The liquid flows out into the crack. When it touches the catalyst particles, a chemical reaction starts, the liquid hardens, and effectively glues the crack back together. It's not as good as new, but it can restore a huge amount of the material's original strength. This could be used in things that are hard to inspect or repair, like an airplane wing or a concrete bridge. A tiny crack could heal itself before it grows into a catastrophic failure. Another approach is to design polymers that can intrinsically heal themselves. Their molecules are held together by special chemical bonds that can break and reform. If you cut a piece of this polymer in two, you can just press the two halves back together. With a little bit of heat or time, the bonds at the surface will reconnect, and the material will be whole again. This is moving beyond just having good properties. This is giving materials a behavior. We are programming them with an instruction. If you are broken, fix yourself. We can take this programming idea even further. This leads to what's called 4D printing. We are all familiar with 3D printing, where a machine builds an object layer by layer. How does it work? You print an object using multiple materials. Some of these materials are smart materials that change shape in response to a stimulus. For example, a polymer that contracts when it gets hot, or one that expands when it absorbs water. You can print a flat object, but you design it with these smart materials placed in very specific locations, like hinges. When you're done, you take this flat object and you put it in a bucket of water. As some parts absorb water and expand, they will pull and push on other parts. The whole thing will begin to fold itself, like a piece of origami, into a complex 3D shape. A flat sheet could fold itself into a box, or a strand could coil itself into a spring. You have programmed the final shape into the material itself. The transformation is the instruction being executed. This can be used for all sorts of things. Medical implants that are shipped flat or in a compressed form and then expand into their final useful shape once they are inside the body. Furniture that assembles itself when you take it out of the box. Solar panels that can be deployed in space, unfolding themselves just by being exposed to the sun's heat. We are teaching materials to build themselves. This is a profound shift in how we think about manufacturing. Instead of forcing a material into a shape, we are giving it a blueprint and letting it follow the instructions. So we have materials that mimic invisibility, materials with impossible strength to weight ratios, materials that are lighter than air, materials that can heal themselves and assemble themselves. What's left? What is the truly impossible? This brings us to the holy grails of materials science. The things that still sit on the edge of what we think is possible and maybe beyond. One of the biggest is a room temperature superconductor. Let's break that down. A conductor is a material that lets electricity flow through it, like a copper wire. But it's not perfect. The electrons moving through the wire bump into the atoms of the copper. This creates resistance. This resistance wastes energy. It shows up as heat. Your phone gets warm when it's charging. Your computer's processor needs a fan to cool it. All that heat is wasted energy, a tax paid to the laws of physics. A superconductor is a material with zero electrical resistance. Zero. Not just a little bit. Absolutely none. If you get a loop of superconducting wire and start a current flowing in it, it will flow forever. It will never diminish. This would change the world. It would mean perfectly efficient power grids with no energy loss. It would lead to ultra-powerful magnets for things like maglev trains and medical imaging, but without the need for massive cooling systems. It would make new kinds of computing possible. The catch is, we can make superconductors now, but only at incredibly cold temperatures. Most of them have to be cooled with liquid helium, which is just a few degrees above absolute zero. This is extremely expensive and complicated. It limits their use to very specialized applications. The dream is to find a material that is a superconductor at room temperature, a material you could just hold in your hand and it would have this miraculous property. For decades, physicists have been searching. They have been slowly finding materials that work at slightly warmer temperatures. They went from a few degrees Kelvin to over 100 degrees Kelvin, then over 200, but that's still well below freezing. Recently, there have been some tantalizing and very controversial claims of room temperature superconductors. A material called LK99 got the world very excited. Researchers in South Korea claim to have made it, and it seemed to show some signs of superconductivity at normal pressures and temperatures. As labs all over the world rushed to replicate the experiment, the results were messy. No one could clearly and definitively reproduce the original claims. It seems that the material was not a true superconductor, but something else that just looked a bit like one under certain conditions. It was a disappointment for many, but it shows how active this field is. The search is on. We don't have a fundamental law of physics that says a room temperature superconductor is impossible. We just haven't found it yet, or more likely, we haven't figured out how to build it yet. It might be another metamaterial where the property comes from a very specific and complex atomic structure that we have to design and construct. What about things that really do seem to break the known rules? What about something with negative mass? This is purely theoretical. Everything we've ever seen has positive mass. When you push on something, it accelerates in the direction you pushed it. If something had negative mass, when you pushed on it, it would accelerate toward you. It would do the opposite of what Newton's laws tell us. This kind of thing would violate other deep principles like the conservation of momentum. If you and an object with negative mass were sitting still and you pushed it, it would accelerate toward you and you would accelerate away from it. You would both be moving and gaining kinetic energy seemingly from nothing. This is why most physicists believe negative mass is not possible in our universe. It seems to be one of those hard limits, but it's fun to think about. It reminds us that our understanding of the universe is still incomplete. We are constantly testing the edges of our knowledge. The biggest challenge with all of these impossible materials is not just inventing them in a lab. The real challenge is making them useful. It's the gap between discovery and application. The first problem is scale. As we've seen with graphene and carbon nanotubes, making a microscopic speck of a miracle material is one thing. Making miles of it or tons of it is another. The processes are often incredibly delicate and complex. Any tiny defect can ruin the special properties. Scaling up production while maintaining quality is a huge hurdle. The second problem is cost. Many of these materials require exotic ingredients, extreme temperatures or pressures, and very slow, precise manufacturing steps. A gram of a new material might cost thousands of dollars to produce in a lab. Until that cost comes down by orders of magnitude, it will never be used in a car or a building. It will be restricted to niche uses in things like satellites or high-end scientific instruments. The third problem is integration. Let's say you manage to make a big sheet of graphene. How do you use it? How do you cut it? How do you join it to other materials? You can't weld it like steel. You can't glue it with normal glue. We have centuries of experience in working with steel and concrete and wood. We have entire industries built around these materials. For these new advanced materials, we have to invent all of that from scratch. We have to learn how to be carpenters and blacksmiths all over again, but at the nanoscale. And finally, there is the problem of durability. A material might have amazing properties when it's fresh out of the lab. But what happens after 10 years in the real world, exposed to sunlight, moisture, temperature changes, and pollution? Will it maintain its structure? Will it degrade? A self-healing material is no good if the healing agent inside its capsules expires after a year. These are the practical, unglamorous questions that need to be answered before a new material can truly change our lives. So, can we make impossible materials? The answer is yes. We do it all the time. But we have to be careful with the word impossible. We can't violate the fundamental conservation laws of the universe. We can't make something from nothing, but we can make materials that were impossible according to the science of 50 years ago. We can make materials that seem to defy common sense. We do it by becoming masters of structure. We are learning to control not just the chemical recipe of a material, but its geometric form at the tiniest scales. We are treating atoms like bricks and building new houses with them, houses with properties that no one had ever seen before. The transparent aluminum from Star Trek. We have something very close to it now. It's a ceramic called Alan, aluminum oxynitride. It's a mineral that, when polished, is a transparent ceramic that is much stronger and more scratch resistant than glass. It's expensive, but it's real. It's used for things like bulletproof windows and lenses for drones. A science fiction trope became a real-world material. This is a pattern that will continue. The materials that will define our future are being born in labs today. They might be metamaterials that can perfectly absorb sound, creating truly silent rooms. They might be thermoelectric materials that can generate electricity from waste heat far more efficiently than anything we have today. They might be new kinds of catalysts that can pull carbon dioxide out of the atmosphere and turn it into fuel using only sunlight. These things sound impossible now. They sound like science fiction, but they are not. They are engineering problems, they are challenges of structure, scale, and cost. And they are the problems that a new generation of scientists and engineers are working to solve. They are not breaking the rules, they are just learning how to play the game on a much, much smaller and much more clever field. The materials of the future won't be found in the ground. They will be designed atom by atom.